friends, Uncle E here with a little discussion about improper integrals. This will be discussion number 2, part 2, improper integrals. Let's get right to it. Hey, let's think about a function, f of x, a function that is continuous, a continuous function on the interval a, b. It's continuous on this interval, including a, and at b, we're going to have some infinite discontinuity at b. So we're talking about a function that is continuous on the interval a, b, including a, not including b, because I have infinite discontinuity right there at b. How do I find this? Well, I'm going to consider, so what I want to do is find this interval right here. Then the interval from a to b of f of x dx, keep in mind this is not a definite interval. It's not a definite interval because we're not continuous at b. We have an infinite discontinuity at b, so we're not continuous at b right there. So this is called an improper integral. Yesterday, on part 1, we defined an improper integral where one of the limits were infinity, or both were infinity. Here, what we have, kind of the same thing. We have an infinite discontinuity at one of the limits, and that's what we have at b. So this improper integral from a to b of f of x dx is equal to the limit as c approaches b from the left of the integral from a to c f of x dx. What in the heck, how in the world did I get this limit? Think about yesterday, more importantly, think about right now today. What we're going to do is we're going to come up with a function that is continuous on this type of interval. Okay, so let's look at that function. And my advice to you, in order to come up with the correct limit to evaluate these improper integrals, is to give a graphical representation of what's going on, and that will help you. And here's my function right here. Here's my function f of x that is continuous from a to b. Well, at b we have infinite discontinuity, i.e. we're going to have a vertical asymptote. And I want to know, does this interval from a to b f of x dx, since it is an improper integral, and it is because I have this infinite discontinuity there, does that integral converge or diverge? That's the key question. In order to find that, I have to create this limit. And what I'm going to do is I'm going to take a c guy to the left of b, to the left of b, and I'm going to take this arbitrary c and I'm going to approach b. And that's where I get this limit as c approaches b from the left. And then I'm going to talk about this integral from a to c f of x dx. Next slide. Close it up. Pull it down. And so, therefore, I have this guy right here. If f of x is continuous on this interval a to b, where I have infinite discontinuity at b, this is equal to that. And this is how I get this. That's what this slide was all about. I take a c to the left of b, same discussion I had, this little graphical representation. And I'm taking c and I'm approaching b from the left right there. That's where I get it. This limit as c approaches b from the left. C is going to be an arbitrary constant to the left of b. So this improper integral from a to infinite discontinuity, I'm going from a real number to an infinite discontinuity of f of x dx. An improper integral is equal to the limit as c goes to b from the left, as c approaches b from the left, of the integral a to c f of x dx. A is going to be fixed, c is going to be this arbitrary fixed thing, this arbitrary constant, and we're going to approach c. C is going to approach b from the left. That's part 2, bullet 1. Part 2, bullet 2. Part 2, bullet 2. If f is continuous on, same interval, same type of interval, except I have my infinite discontinuity at the left-hand side of this interval. So I'm going to have my infinite discontinuity here is going to be at a, and I'm going to include b, and so I want a function that is continuous on this interval, including b, and up just to the right of A. And I'm going to have infinite discontinuity at A. This is not going to work where you have jump discontinuity at A. It has to be infinite discontinuity at A. And here's what I have. Here's the formula to find, again, this is going to be an improper integral because I have an infinite discontinuity right here at A. And so I'm taking this integral from infinite discontinuity A to be a constant of f of x dx is equal to the limit as c approaches A from the right, of c to be f of x dx. Whoa, last one off to the left, down to the right. Let's look at the graph and see where this comes from. Oh my gosh, calm down a little bit. Well, here you go. Right here. Here's my function. F of x. Look, I have infinite discontinuity at A. At this B. And I'm going to talk about this. And I'm going to talk about that guy right there. And I want to find out. I want to find out if this guy here converges or not. And so I'm going to look at this improper integral from A to B of f of x dx, where A is infinite discontinuity, some asymptote thing going on. And that's going to equal the limit as c goes to A from the right. And what you're going to do is you're going to choose an arbitrary c just to the right of A. You're going to choose a c, a constant, just to the right of A. And you're going to take that c and you're going to keep getting closer and closer to A. I.e., you're going to take the limit as c approaches A from the right. You're approaching A from the right. And therefore, this improper integral is going to be the limit as c approaches A from the right, from c to b, f of x dx. Enough of this theory, let's do an example. Example number 1. Let's talk about that function right there, f of x is equal to 1 over quantity x minus 2 squared. And what we're going to do is graph this function. You should be able to graph this easy rational function. Pretty easy. The first thing you know is, hey, the domain does not contain 2. So if something happens at 2, there's going to be an explosion at 2. The graph is always going to be positive because 1 is always positive. Something squared is always positive. 1 divided by positive is positive. 1 is never 0, so I have no x-intercept. As x gets big, that guy's going to get really small. As x gets big negative, that guy's going to get really small. Both go to positive 0, positive 0. Y-intercept, if x is equal to 0, that's going to be negative 2 squared 1/4. It's going to be 1/4. So it's an easy graph to graph. And right there it is. And what I'm going to consider this time, there's the graph in blue of f of x. It looks like I'm going to consider this integral from 2 to 4 of f of x dx, and let's do consider that. So this is the guy that I want to consider. I want to consider the improper integral from 2 to 4 of 1 over quantity x minus 2 squared dx. And this is improper because I have this infinite discontinuity at 2. Please don't make this difficult. And that's going to equal, this improper integral is going to equal the limit as c approaches 2 from the right. C is going to be an arbitrary. You could use D, E, F, G, Y, N. But let's just use C because they told us to. And C is an arbitrary guy to the right of 2 since I'm going from 2 to 4. And what I want to do is I want to take C as it approaches 2 from the right of the integral from C to 4 of 1 over quantity x minus 2 squared dx. First thing I'm going to do here to evaluate this is I'm going to figure out what that guy is. What the general antiderivative of 1 over quantity x minus 2 squared is. That's step number 1. In order to find that, that's what I'm going to find. So that's what I'm going to do right here. I'm going to find this general antiderivative. 1 over quantity x minus 2 squared dx is going to be the same as x minus 2 to the negative 2. And if I would do substitution with this, u is x minus 2, du is dx. So I can just do the straight anti-differentiation. I'm going to add 1 to negative 2. Negative 2 plus 1 is negative 1. Divide by negative 1. And x minus 2 to the negative 1. And that's going to equal negative 1 over x minus 2. That's the general antiderivative of this guy right here. I'm going to put this general antiderivative, and I'm going to use the So the general antiderivative of this guy right here is negative 1 over x minus 2. And now I'm going to use the fundamental theorem of calculus part 2 and evaluate this dude right here from c to 4. I'm going to evaluate that antiderivative, negative 1 over x minus 2, at 4, and subtract from it that antiderivative at c. Antiderivative at 4 minus antiderivative of c. Then I'm going to take the limit of c goes to 2. Well, if I put 4 into that guy, if I put 4 into that, 4 minus 2 is 2, so I have negative 1/2, plus, put c into that, negative, well, it's going to be minus negative, that's what makes this guy here positive, over 1 over c minus 2. And as I take c, so as c approaches 2 from the right, where does this guy go right here? Well, if I'm approaching 2 from the right, let's say it's 2.000001 minus 2 is 0.00001. 1 divided by that little big thing is going to be a great big giant thing. And so that's going to be negative 1/2 plus a great big giant thing is a great big giant thing. And so therefore this guy diverges, and I want to end with the appropriate statement. The appropriate statement in this case is the improper integral from 2 to 4 of 1 over x minus 2 squared dx diverges. Because that's what we want to know. Do these improper integrals diverge or converge? Keep in mind the series test, the improper integral series test. Does the series diverge? Does the series converge? This one diverges. Let's do another example. Example number 2. Example number 2, let's consider the integral from 2 to 4 of 1 over x minus 2 to the 1/2. 1 over x minus the square root of x minus 2 dx. And let's graph this guy right here. And we're going to take it from 2 to 4. And we see at 2, this guy doesn't exist. It has infinite discontinuity. There's a vertical asymptote. Well, the other thing we want to notice is that the square root always pops out a positive. So this guy's always going to be positive. It's not going to be positive. The domain is going to be greater than 2. So it's only going to exist. This function is only going to exist to the right of 2. And so if I look at the graph of that, there is the graph of 1 over quantity x minus 2 to the 1/2 power. So this integral represents this guy right here. From 2 to 4, and I have infinite discontinuity at 2. The thing explodes as it goes to 2 from the right. And that, if I graph this, that's going to give me an easy way to figure out what limit I'm going to let this improper integral equal. Okay, so what am I going to do? I'm going to take this improper integral, infinite discontinuity at 2 from 4, 1 over x minus 2 quantity to 1/2 power dx is equal to the limit is c. I'm going to take a c right here to the right of 2, and I'm going to take c and I'm going to approach 2 from the right. Of the integral c to 4 of 1 over x minus 2 to the 1/2 dx. Step 1, just like I did before, I'm going to find this general antiderivative right there. I'm going to find the general antiderivative of that and then use the fundamental theorem of calculus. Let's do it. Okay? Ho! Hang on there, Chief. Woo, where am I? Right here. Right here. So I'm right over here. I want to find the general antiderivative of 1 over quantity x minus 2 to the 1/2 power. Again, I'm going to write that as x minus 2 to the negative 1/2 power, and I'm going to anti-differentiate that. I don't have to use a u substitution here because the derivative of the inside is simply going to be 1. So I'm going to use the anti-differentiation rule. Negative 1/2 plus 1 is going to be 1/2. Divide by 1/2, that's where this 2 comes from. Negative 1/2 plus 1 is going to be 1/2, that's where this 1/2 comes from. So this is the general antiderivative of this guy right here. So now I'm going to use the fundamental theorem of calculus on this rascal here. So this dude here, the limit as c approaches 2 from the right of the integral from c to 4, 1 over x minus 2 to the 1/2 dx, is equal to the limit as c approaches 2 from the right. That's the antiderivative of this. And if I put 4 in, 4 minus 2 is 2. 2 to the 1/2 is the square root of 2, so I have 2 square root of 2. Now if I put c in, I get minus 2 times c minus 2, the square root of c minus 2. Now I'm going to evaluate the limit if I can. And I notice as c approaches 2 from the right, where does the square root of c minus 2 go? Think for a moment. Okay, stop thinking. Where does that go? As I'm approaching 2 from the right, that guy's going to 0. The square root of 0 is 0, 2 times 0 is 0, so this is simply going to be 2 square root of 2 plus 0, which is 2 square root of 2. Nice! So this limit exists. Nice! So this improper integral converges. And that's what we want to do. We want to finish our statement with that, because that's going to be very important, because this is the objective. The objective here is to, hey, does it converge or diverge? This is going to be of little importance, not little importance, but not as important as does it converge or does it diverge? And here I have an improper integral from 2 to 4, infinite discontinuity of 2. The integral of dx converges to 2 square root of 2. Please don't make this difficult. Good day.